Here we'll look at the Bellman-Ford algorithm, which will find the shortest paths from a single source S, even if there are negative edge weights. In Dijkstra's shortest paths, we can't find the shortest path from S to C if we pop B off a priority queue and update this before we look at this edge, right? Before we look at A, if we already look at B first, we won't have the correct shortest path to C because we won't put B into the priority queue. When we pop this off our priority queue, we assume that B is already we already found the shortest distance from S to B, right? So now in this, for fix, we look at the Bellman-Ford algorithm, which for every single edge, we're gonna make an update, which is the same as the Dijkstra's update equation, such that we do this V minus 1 times. And the reason we do a V minus 1 times is because in the worst case, there's the distance furthest away from S is going to be V minus 1 edges away, right? So in the first iteration, in this case, we'll update this vertex, second this vertex, and finally in the last iteration, we'll update this vertex. Note that, however, if it was something like this, then you found a shortest path in 2 iterations, and doing one more update shouldn't change that. There will be a situation where that changes, but we'll see later on in the video. So now let's kind of go through this example up here. We initialize the distance as infinity and the previous values as null. So in the first iteration, we're going to update S to B. S to B is going to get a result of, let's see, 2, right? And we have 2 here. Our previous value is going to be S. Now we look at B and C. B and C has 1. The distance of B has updated to 2, so we add it to C's distance as 3, and we get now B. Now we look at A and B. A and B is going to give us negative 5. So negative 5, but the shortest distance from A to A is still infinity, so this won't change. So B, that's not going to change anything. S to A, now we can update this edge. We're going to see that with 0 plus 3, and here with S, and this stays 0 all the way out, right? So notice that if I had updated this edge, and then this edge, we would have gotten the correct distance of 3, negative 2, and then negative 1, right? But we did it in this order, and so we need to make multiple updates before we can get this fully correct. Now let's look at the second iteration. We update S to B. That's not gonna change anything, so we stay as 2, right? And this is just stay as S. We look at B to C. Again, nothing changes. So here we have 3. But now when we look at A and B, since I updated this to be 3 previously, I now have a small distance of negative 2 rather than the 2 to B, right, if I go through A. So this becomes negative 2. This becomes A here, and this is going to be negative 2. Now I can update S to A, nothing changes, so we can keep this as it is. Now in the final update, notice that in the last iteration, I've updated the shortest distance to B, and this does not propagate through yet because of our order. So now in our final update, we can make an update to S and B. Nothing's going to change. B to C, now that when we look at this edge here, we see that the distance to B has decreased to negative 2, so we get a negative 1 to C. Negative 1 here. Negative 1. Oops, sorry. It's negative 1 down here, and then this is still going to be B. Look at A and B, nothing's going to change, so we're going to keep this as A. And this is going to be negative 2. And finally, S to A, we're going to keep that as 3 and S. So we now have successfully found the shortest path from S to all these 3 nodes, despite having a negative edge here, right? This is going to be 3, negative 2, and then negative 1. Now let's look at figure 2. In figure 2, we have this cycle, and we're going to show that after V minus 1 iterations, if we do one more iteration, one of these distance weights are going to decrease, letting us know that one of these vertices part of a cycle. And we can trace through the cycle using the previous pointers. Right? We're going to maintain the same update order. We can look at these going to be 0. So we look at S to B. Oh, let's see now. We need another update order. Let's see. Let's do A to B, B to C, A, B, C, and then B and A, right? So I just picked this update order arbitrarily. It doesn't really matter. It only matters for the middle iterations. It won't matter at the very end where it will, the distance here, the shortest paths distance should not be dependent on my edge update order, right? You can do it alphabetically, you can do it arbitrarily, it doesn't matter. So let's get started. We have A and B, we have an infinity, so this still stays as infinity. C to A, again, we have infinity, so we keep it as infinity. S to A, now we see that we update it to 3. Oops, so this was updated to infinity from C to A. Now we update this to 3. And S to A, and then we look at B to A, A to B. Hold on, sorry. B to C over here. So now we look at B to C, it's still going to be infinity for C as B hasn't changed. Right. Next iteration, we can look at A and B. Now that A is updated to 3, we have 5. C to A is still going to be infinity, but we have 3 here. S to A is still going to be 3. And then BC now it's going to able to get me to negative, 3, right? Because of now we look at this again. AB, nothing changes. CA has now, because this, CA, now that this has decreased 3, we take a negative 2, and we can do a 1 over here. SA, 3 is larger than 1. You don't want to update. And then BC, 5 negative 2 is still going to be 3. Now that we have our shortest paths, remember that if we have a negative cycle, this last iteration will change depending on the order we update, because one of these vertices will have we don't know which one of these will decrease at this iteration, right? Because if I found a shortest path at some middle iteration here and I keep making 1 updates, one of these, the negative cycle is going to propagate through each of these vertices in each iteration. So the edge order won't matter for something that don't have negative cycles, because at the end, like v-1 iterations, we will have the shortest path from S to every other node. But whereas if we have negative cycles, you can't, like this is like v-1 iteration won't necessarily be the same, because we could have found the shortest paths somewhere earlier, and then that last update is going to give us a negative cycle. But since our algorithm always does v-1 times, we have to make one more update to find this negative cycle, right? We know that after 3 iterations, S should have found the shortest path to every other vertex. So now let's make one more update. With A to B, A has now be negative 1. 1 plus 2 is 3. So we have decreased at B. CA won't change. SA won't change. And then BC now gets updated as well. Right? We have 3 minus 2, we get 1. So we see that both B and C both change. So we know that both of them are in the same negative cycle. And we can just trace back the previous value to find that A is also in the negative cycle. Right? So negative cycle means that if I keep taking the cycle along, my shortest total cumulative path distance is going to keep decreasing for like total vertex. So if I go A, B, C, and so on and continue, my total is going to keep decreasing in every iteration.